So we started talking about calculations in rotating coordinate systems, particle kinematics in rotating coordinate systems. And so does anyone remember what was the operation that causes problems when you go to a rotating coordinate system? It's taking time derivatives. Any time derivative of a vector causes problems in rotating coordinate systems because you have those product rule terms, remember? So if you have a vector u and you take the time derivative, you get this, which is what we expect, but then you also get this because of the product rule. Mm-hmm. And this is where all the problems come from, okay? And so I went through like a little geometric argument for why you can believe that the big result is true. But remember that what the big result that we're going to use for everything was a way to calculate the time derivative in a rotating coordinate system. What's that u vector? It doesn't matter. It can be any vector. It can represent anything. It can represent force, position, whatever. Okay? If you want to take the time derivative, you have to use the big result. It's the only thing that I call the big result in any class I teach. So you know it's important. The big result says the time derivative, I mean, these are the same, right? The time derivative of u is the time derivatives of the components plus omega cross u. Or equivalently, just depending on what form you have this stuff in, you can write it as u dot is equal to what the camera, the coordinate system camera, sees as u dot, plus this stuff that the camera can't see that you can calculate that way, okay? And the big result led to expressions for the velocity vector and the acceleration vector, which are obviously, especially acceleration, these are really key things in kinematics, you know. Acceleration is super key because remember, that's the skyway that connects kinematics to kinetics, you know. You gotta, even if you park on floor 7, you gotta take the elevator down to the skyway to get to the other building. That's what acceleration is, you know. So, and these results are that the velocity is equal to the components of position dot So the velocity vector looks just like the big result because all we're taking is one derivative, you know. And so you got the derivatives of the position components plus angular velocity of the coordinate system crossed with the position vector. Or you can also write that, depending on how you're given this information, velocity is equal to the velocity that the camera, the coordinate system, sees, plus the part that it doesn't see, which is this. And then the acceleration is much more complicated, and unfortunately it's the one that's most important to us because it's the skyway, is the time derivatives, second time derivatives of the components of position plus omega dot crossed with position vector plus 2 times omega crossed with the component's single dot of the position plus omega cross quantity omega cross p. Or you can also write it as acceleration is equal to the acceleration that the coordinate system sees plus omega dot cross p plus 2 omega cross the velocity that the coordinate system sees plus omega cross quantity omega cross p. Okay. Most often we're going to use this form, this one and this one. That's just most often what's going to be available to us. But when would you use the other one? So, for example, when would you use the component dot form? And really, the answer to that is just any time that your position is given as a function of time. So when you know position vector as a function of time. Okay, so like let's say that the rotating, according to this rotating coordinate system, the position vector is equal to t squared cosine t 5t. And the coordinate system has an angular velocity of, so this is our omega, and it's equal to, let's say, 10 to negative 6. Okay, so in this case, let's say this is constant. Well, the velocity vector then, we're going to use the form where this is the components dot plus omega cross p. And so this is equal to 2t negative sine t 5 plus 10 to negative 6 crossed with the position vector now all you have to do is do that cross product and add those up, and that gives you the velocity in that the inertial coordinate system velocity using that rotating coordinate system. Okay. So, you can multiply that out. So let's say we just wanted to calculate the velocity. This is how you would do it. Same with the acceleration. You just take the second time derivatives and stuff. Okay. And then the key thing is, so if we didn't know this about rotating coordinate systems, that there was this complexity to it, we would maybe just think that the acceleration was just the second time derivatives of the components. That's what we're used to doing in a non-rotating system, right? Okay? Someone nod. So you'd say, okay, well, that's the acceleration, maybe just the second time derivatives of those components. But if then you tried to put that into Newton's second law, it wouldn't work. You'd get wrong answers, okay? This, if you calculate your acceleration this way, put it into Newton's second law, everything works. Yep.
So to get acceleration, you could you could use the big result on your dot operator.
Yeah.
Or you could calculate it directly using the formula we found.
Right, exactly. Remember, we these two formulas, that the velocity and acceleration formulas, I derived that last time. So yeah, you could say, like, if you're cool, if you want to be cool, just say like, oh, I don't remember stuff, I just derive stuff, and like all I know is the big result. You tell me what you want a time derivative of, and I'll do it, And the acceleration is just doing it twice. Now, I know this is super weird and it's going to feel uncomfortable at first and things will not make sense at first, but does anyone have any questions right now? Hopefully, as we just keep grinding through this stuff, the things that are confusing will just little by little sort of clear up. Okay. Well, one thing I want to do now is I want to use this rotating coordinate system approach to calculate the velocity vector and acceleration vector in polar and cylindrical coordinates. I'm going to more emphasize polar, but they're really the same. The cylindrical coordinates just have kind of a separate z thing going on. Okay, so the first question is, why would you ever want to use polar coordinates? And the answer is that for some shapes, some paths of an object. This is just, polar coordinates are just an easier way to represent things, okay? So for circular related shapes, I'll show you what I mean by that. Conic sections. There's some other things. I mean, maybe if you think way back to junior year of high school or something, you talked about cardioid shapes and all these funky shapes you can do in polar coordinates. They're just things that are simpler in polar coordinates than in rectangular coordinates. So for circular related shapes, conic sections, some other stuff. The math is just easier in polar. For example, let's see, where did I put this thing? This shape. So let me, it's based on a circle. So that's like my guideline circle. And then okay, a shape like that. Imagine trying to do that in rectangular coordinates. In polar, this just has the form r is equal to 5 plus cosine 8 theta. Why would you ever want to do this shape? I don't know. But if you ever happen to see a shape that had like a circular base with these fringes on it like this, and these are like sinusoidal fringes that I'm using, then imagine what that would look like in rectangular. This is what it looks like in polar. It's just so simple. And what about an ellipse? Well, it's not always like this is the easiest way to do an ellipse, to deal with an ellipse, but elliptical motions are important in dynamics, right? Because of orbits. So an ellipse like this, the rectangular formula for an ellipse is kind of a pain, but the formula for this is just r is equal to, this one's 0.8 over 1 minus 0.8 cosine theta. Just nice and simple. The problem with doing dynamics, the problem with using polar or cylindrical coordinates with dynamics is this. R theta, those are the two coordinates, is not a vector. And so you can't just take time derivatives of this and expect to get velocity, you know, and take a second time derivative and expect to get acceleration. Sorry, it's not a position vector, let's say. This isn't one component along one axis and another component along another axis. So you can't take just time derivatives to get velocity and acceleration. Okay, so what do you do? And so now I'm going to derive expressions for the position vector, velocity vector, and acceleration vector in polar coordinates so that you can do dynamics on, so say you happen to be working on a problem where you have some shape that makes sense in polar coordinates. You can use that to calculate velocities and accelerations. Okay? Anyone still listening even? Everybody's just thinking about like, I wonder what's gonna be on The Simpsons on Sunday. Okay, so here's a derivation of a position vector, velocity vector, and acceleration vector using polar or cylindrical coordinates. And we're doing this now because this derivation is going to use the rotating coordinate system idea. Okay, so let's say we have this sort of underlying, you know, with this stuff, there's always an underlying inertial coordinate system that everything's taken relative to. We don't really talk about it or draw it for the most part, but what we're always doing is using our rotating coordinate system to figure out what a velocity or acceleration would be in an inertial coordinate system. Okay, so there's always this underlying thing. So I'm going to draw the underlying inertial coordinate system. You can think of it like that. And then the object's moving through space like this. And we are going to use a coordinate system. So this is the position vector. And we're going to use a coordinate system where I'm going to call this the R axis. And 90 degrees from that is going to be the theta axis. Yep.
I think we're on the wrong page.
Yeah.
Oh, what am I doing? I'm just...
We're in 4-8 instead of 4.
I think you just switched before drawing the diagram.
Oh, thank you. I would have never figured out what happened there. Shoot. How far back do I have to go here?
Not super problem.
Okay. Don't confuse. Okay. Thank you.
It's just the diagram.
Okay, just the diagram. That's excellent. Thank you. I'm very glad we did that now. Okay, so this wavy line is supposed to represent the particle's motion. This is the coordinate system we're going to use. And so notice that this ER axis always points directly at the particle. And the angle theta is from our underlying XY coordinate system to the R axis. Okay? So in this coordinate system, how do you represent the position vector? That doesn't take any time derivatives. If that ER axis always points at if that ER axis always points at the particle, then I think you'll agree it makes sense that the position vector is just R in the ER direction. Okay, so I mean that thing just keeps pointing at it wherever it goes. So so the position doesn't have any E theta component. Okay. And I'm going to write these this way. You can see that, so if you imagine like a z-axis pointing out towards us for both of these two coordinate systems, the polar and the xy z coordinate system, we can think of ER as our first axis, E theta as our second, z as our third. And so I'm going to write this as R in the first axis position, 0 in the second, and 0 in the third. Okay, so the first one is always going to be our ER location. The second one is always going to be our E theta. And this is always going to be our EZ, which is funny because it's always also going to be the EZ coordinate. And so the only difference is, I'll show you at the end, but in polar coordinates, we don't worry about a z component for anything. That's only there for cross products and angular velocity vectors and stuff like that. When we go to cylindrical, that'll just be a z component that's independent of those other two. Okay, so now the velocity vector is equal to the position vector, and I'm going to notice my subscripts are going to be different now because we're using this ER, E theta, EZ thing. So our velocity is going to be the time derivatives of those components. Plus the angular velocity of the coordinate system crossed with the position vector. And what is this angular velocity vector? Well, so what determines how fast this is rotating? What determines it is the time derivative of theta. And notice that theta is a rotation about the z-axis. The z-axis is out towards us. So this is just going to be 0, 0, theta dot. Okay, so now this velocity vector, plug in the values, you get r dot 0, 0. I'm just bringing down the position vector and taking those time derivatives. Plus 0, 0, theta dot crossed with r 0, 0, the position vector. If you take this cross product, that comes out to be 0, r theta dot 0. Let me do that in red for later. So this is 0, r theta dot 0. And so our total velocity vector is just equal to r dot, r theta dot 0. Okay. Which is the same thing as r dot er plus r theta dot e theta. Okay. And then the acceleration is the second time derivatives of the position components plus omega dot crossed with the position vector plus 2 times omega crossed with the first time derivatives of the components. That should be PR. Plus omega cross quantity omega cross P. And so the acceleration is equal to, take the time derivatives of our position components. This is r double dot 0, 0. Plus omega dot is 0, 0 theta double dot. You see that? Because our omega vector was 0, 0 theta dot, so this is just 0, 0 theta double dot, crossed with r 0, 0, plus 2 times 0, 0 theta dot, crossed with r 0, 0, plus 0, 0 theta dot, crossed with the quantity 0, 0 theta dot, cross r 0, 0. Yes?
Wouldn't it be r dot for the vector right after the two?
You're right, it is. Thank you. Thank you. Okay, so this comes out to be 0 r theta double dot 0. This one comes out to be 0, 2 r dot theta dot 0. This one is 0 r theta dot 0. And so all of this together is negative r theta dot squared, 0, 0. And so you get an acceleration vector of r double dot minus r theta dot squared. Then for the y component, the theta component, r theta double dot plus 2r dot theta dot. So in polar coordinates, this is kind of like the punchline, the take-home message. The position vector is r0. We only care about the r and theta axes, where this is your er and this is your e theta. The velocity vector is whatever I said before, r dot, and then r theta dot. And your acceleration is r double dot minus r theta dot squared. And then your second component is r theta double dot plus 2r dot theta dot. Okay. So for one thing, I wanted to show you, how to, just another example of applying the rotating coordinate system approach. But then also now these are just formulas you can use for polar stuff and cylindrical stuff too. So let me just write, you're just gonna have to trust me on the cylindrical. I'm not gonna go through it again with a z-axis, but nothing really changes. The z-axis is independent because the rotation is happening about z. So in cylindrical coordinates, it's just the same. Just include a z-axis. So you get a position vector that's equal to r0z. A velocity vector that's r dot, r theta dot, z dot, and an acceleration vector that's r double dot minus r theta dot squared, r theta double dot plus 2r dot theta dot z double dot. Any questions about that? Okay, well, let me just do the simplest example possible. Let's say we have, well, let me do an example that's pretty simple, but I'm going to put one little extra thing into it. So let's say we have a circular path, so we have a particle moving in a circular path with a variable speed. Or not a variable, but a varying speed. So let's say that, so if it's in a circle, our r is just going to be some number, right? And if the speed is varying, let's have it vary as a sinusoidal function. So let's say theta dot is going to be equal to 2 minus cosine of t. Okay. That says that, you can integrate that to get the theta function. So theta is equal to 2t minus, we're integrating, so minus sine t. Okay, so what that's saying is, this thing is moving around a circular path, and it's going fast here. No, it's going slow here. Fast here. Fastest here. Okay. Yes.
Why did we define theta dot?
Because just in my head, I was picturing I want the speed to vary, so it was easier for me to just come up with an expression for how fast it's moving around this circle and then figure out theta from that.
Okay.
But, so really our starting point is just this r and this theta, But I just wanted it would be too boring if it was just going the same speed the whole time around,
Yeah, okay.
Okay, so so let's say we want to calculate the acceleration. So to do that, we're going to need some time derivatives of these values. So r dot is 0. R double dot is 0. Theta dot, that actually was what I started with, so that's this. And theta double dot is sine of t. Right? So I'm not saying right like, do you get it? When I say that, I'm like, I didn't make any mistakes, right? And so the acceleration is, the formula we have for the acceleration is r double dot minus r theta dot squared 2 r dot theta dot plus r theta double dot. Now just plug these values in and you get 0 minus, what was our r, 5? 5 times 2 minus cosine t squared. And then for the theta component, 2 times, well, this is all 0. Plus 5 sine t. So we got 5 times, I'll just leave this squared, 2 minus cosine t squared, and then 5 sine t. And this particular motion, I mean, I sort of pulled this motion out of thin air, but this particular motion would be a real pain to calculate this stuff for in rectangular coordinates. But it's pretty simple in polar, you know. And so now what if you wanted to use this to, so remember this is your ER component, this is your E theta component. What if you wanted to express this acceleration now in that sort of underlying XY coordinate system? How would you do that?
Can you use a rotation matrix?
Yeah, exactly. That's what you would do. Use a rotation matrix where the angle for your rotation matrix is just that theta. Okay, so what I'm trying to get at there is, okay, we have a vector that at every instant will satisfy Newton's laws. This is an inertial acceleration. But remember that at every instant, we're using a coordinate system that's with the r-axis pointed at the object. So you have to account for that rotation if you don't want it. Okay.
Did we drop that negative moving to the bottom?
Yes. Oh man, Philip will never know. Okay, any questions about that? Okay, I think there's one problem I can give you related to polar coordinates, but then next time we'll get into the stuff where we can start really doing problems. But come on, this is cool, right?
It is fun.
Yeah. You're taking, like, we're basically like undoing that Jamiroquai video, you know? Like, you know, where he's like sliding around and stuff. And we're saying like, okay, just tell us something about the motion of the house, and then we'll figure out what he's really doing.